Yes, I'm Martin Swany from, most recently from Indiana University, and Ezra Kissel is my PhD student still at the University of Delaware. Both of those things will be not true soon, in that he's nearing his graduation pretty soon. Next slide, please. So briefly, just to introduce what we're going to be demoing today, and to say a few other things. We're going to be talking about, as Mark said, XSP, the Extensible Session Protocol, and two related approaches, Phoebus and slabs. We'll also be using our Genie instrumentation and measurement project tool called LAMP. There were a lot of questions about that last night, so I just want to say briefly talk about that. And then to talk about a little more about the demos. As Mark said, we'll be demoing here, and you've seen some of the demos today that will be reprised in a couple of weeks at SC11. And I want to note that SC is actually the conference formerly known as Supercomputing. It formally changed its name, like Prince, due to a contract issue, I guess, or not really. Actually, it changed its name for us. In fact, it's now the Conference for High Performance Computing and Networking initially, and as well as storage and analytics. So it's a good venue for this sort of work. And the SciNet Research Sandbox, the SRS, will have open flow switches from HP, IBM, NEC, and Pronto, as well as some wide area 100 gig experiments. I'm co-chairing that effort along with my colleague Brian Tierney at ESNet. So it's very exciting. And then also, the Disruptive Technologies program will have feature a talk by Mark Berman, who some of you have heard of. So that promises to be exciting as well. So next slide, please. XSP is really the core of this demo, and I should say also it's supported as a Genie experiment by the NSF. And the idea behind XSP is that it's a session protocol, a layer 5 protocol, which you learned about a long time ago in your first networking class and then promptly forgot, as the internet thus far hasn't really had a cohesive one. So the session protocol in our model addresses the need for the end-to-end context that the end-to-end argument and tells us that we need to have, that end-to-end context. But it allows for innovation at various points in the core. So we're sort of backing off the binding of end-to-end communication from the transport protocol to the session protocol, and allowing us to do different things below that. So we have a socket-compatible library, a shim library for legacy applications. We'll also talk about another library that you can use to expose more of the features in the session layer. So the in-band and out-of-band signaling that this affords us by adding this to the model of communication gives us some interesting properties. Namely, it makes it really ideal for dynamic or software-defined networks. So rather than something in the network figuring out that it needs to install rules, we have the application explicitly saying, hey, we're about to do something, set things up in the following way, and that gives us a lot of power. So it's, there's also a channel for data to be forwarded with session layer frames, and we'll talk a little bit about that in a minute. I'll say the session protocol has other benefits for the future internet, and these are some other things that we're exploring, not directly related to this demo, but binding this end-to-end context to a session lets us do things like location identification separation, so you can make a session connect to an abstract entity and let the network details be sorted out or possibly change over time. Because we have this explicit sort of call setup step, we can do interesting things with authentication and authorization. So we currently are able to authenticate with X509 or with SSH credentials and dynamically establish rules in the network, so essentially acting as a dynamic firewall or a default off sort of model in which the users are allowed to forward not based on their IP and some ACL, but really based on their identity, which is a nice property. Next slide, please. Oh, I see, we've got Got pages of text, things are happening, good things, good. Okay. Today, what we're going to demo is Phoebus and slabs. So Phoebus is a project that we've been working on for a while to address performance concerns in high-performance networks. And so it uses XSP to enable adaptation points in the network, accelerators, protocol gateways, translation gateways, essentially. And achieves really good forwarding performance, 10 gig or above for TCP. It's interesting that in the time we've been doing this, a market has sort of sprung up, $2.5 billion in the market last year for techniques called WAN acceleration. So what we're doing, you know, what we used to say, all of these things to say what we're doing, now we can sort of just say, it's a WAN accelerator. But it is a WAN accelerator, but it's actually distinct in that it's a principled approach and an architectural model that adds this to the network rather than a black box that does magic things for your you know, enterprise network. Slabs basically applies burst switching context to the Phoebus gateway. So essentially we call it session layer burst switching, and the idea is that, as you can see at the bottom, various connections are set up. The Phoebus gateway is buffering data over time. Once the buffers, we have a sufficient amount of data, then we can allocate a circuit or insert some open flow rules and burst across that new link at line rate very aggressively, and then close the link and essentially consider that one session layer PDU, which we refer to as a slab. And we also use slab in the verb sense here, which is the XSP is reframing or slabbing these individual conversations together into a large PDU that can really take advantage of a high-performance link that's been allocated. Right. So, and what we're going to show today is minimizing the total transfer time of bulk data flows. And so this talks a lot about IP networks, but it's interesting to note as well that it doesn't require IP to be used in the core of the network. So we have a situation in which an end host is making a traditional connection, TCP IP connection, and in the core of the network, the Phoebus gateways are translating that to a lower layer or different protocol. So we're not demoing it today, but at SC we'll be demoing this using the Open Fabrics RDMA protocol, using RDMA over Ethernet, Rocky, in the core of the network, while the edge systems are actually still using TCP IP. Next slide, please. Is that timer related to how long I've been talking? Okay. Okay, good. I get to know. But it's counting down. Oh, good. Okay, so I'm not going to say anything about Periscope. There was we did a demo last night, please join us in the I&M sessions this time or next time. Ask us questions. Other experimenters, we'd love to have to help you use Periscope in your Genie experiment. Next slide, please. Briefly, the SRS demo. No, even more briefly. The only difference between what you're seeing today, the primary difference in the demo in 2 weeks, is that we'll be doing this with 10 gigabit links and using RDMA, as I said. So with that, next slide, please. And you can maybe talk through the thing, and I'll go. Sure.
Yeah, I think we're running out of time here, so I'll try to keep this short as possible. But our demo architecture involves exactly what Martin just talked about, which is the idea of having an XSP control plane to manage various dynamic network services that exist within the network. So we have a standard interface for configuring network rules, and then these back-end modules will talk to an open flow switch or talk to an IDC to configure those networks for us. And next slide, please. So what I'm going to talk about in our demo is what we've actually been able to implement on the Genie architecture. So we're typically involved with 10 gigabit per second or beyond networks. On the Genie architecture, we're dealing with gigabit per second or so. But we can apply the same principles and show some decent results. So the resources we've been able to use include the Proto-Genie backbone nodes, as well as some existing backbone nodes we have on the Internet 2 network. And we use ion circuits to connect both the Internet 2 backbone and the Proto-Genie backbone. We've also incorporated open flow resources that exist at the GPO lab. And we're using a number of grid FTP transfers as our typical application for moving bulk data. And the idea is we create dynamic circuits on behalf of the application, and once those are available, how do we best utilize the resources that are now brought up for the application transfer? So what I have here on the other screen, and if we could now get the Periscope interface up on the projection here, we can actually show the demo in action. And unfortunately, okay, so here is the Periscope interface, which is part of the LAMP project, allows us to visualize the topology that exists. And we can see that there are active transfers running right now that I've started previously. And this transfer in particular is between Stripe Grid FTP servers on the West Coast. And unfortunately, we're not getting a full screen view here, but they are going to Grid FTP servers on the East Coast following an ion circuit that's been established between the Internet 2 backbone and the Protogenie backbone. And we're using Phoebus to optimize the transfer over the backbone network itself. And in this case, we're using protocol adaptation to move from TCP to a UDP-based transfer and being able to rate limit, because the Grid FTP servers on one end are able to provide much better bandwidths, close to 10 gigabits per second, and they're trying to push it through a 1 gigabit per second backbone in the case of this Protogenie or Genie experiment. And the fact that we're able to rate limit it allows us to get much better performance over the backbone network. As you can see in this graph that just came up, I have some experiments that are showing the sawtooth pattern, and once we rate limit, we're able to see very consistent performance over the backbone. And let me see if the other aspect here is to actually bring up a dynamic circuit on demand, and unfortunately the screen is a little hard to see here. But let's see if we can bring up the ion circuit on demand and bring up an open flow pass that we have established at the GPO lab, which is indicated here on the Periscope interface. So let's give this a shot. So here we use a Grid FTP client utility called Globus URL copy, and we're moving parallel streams from, in this case, PC5, which is a Protogenie host at the GPO lab, and we're moving it to, or we're trying to transfer data to PC150, which is a Utah Emulab PC. So what this allows us to do then is we can specify exactly on the Grid FTP client command line where the XSP daemon is running, where we can actually configure the dynamic network pass and specify what type of pass rules we'd like to establish. And in this case, we are going to use the default configuration, which means we're going to install OpenFlow pass as well as bring up the ion circuit dynamically. And you can see now that I instantiated this transfer on the Periscope interface, you see a blue link show up between PC5 and the GPO lab Protogenie resources. That means those rules have been installed, and let me see if I can make this bigger. You can actually see the controller that has added those OpenFlow rules from that IP address to these destination IPs that are being used for the dynamic pass. And what's happening now is that the XSP daemon, our controller, is also contacting ION to set up a dynamic circuit between the GPO lab, the BBN endpoint, going to PG41, which is the Protogenie Washington endpoint on the Protogenie backbone. And you can see here that the reservation has been accepted, and it's now in a pending state. And it's going to, unfortunately, take a little while for that circuit to come up, typically 30 to 45 seconds. So I don't know if we have time to wait or not, but what would happen is once this circuit becomes active, we'll automatically have the transfer start. The daemon actually contacts the client and says the circuit or pass is now ready. The transfer will begin, and we're able to see it visualized on the Periscope interface.
Yeah. Why don't we let this run for another minute or two while I introduce the next demo, and we can sort of see the end play out. And that will be Aaron Rosen, who's coming up from the back. So Aaron's from Clemson, and Aaron's going to demonstrate the steroid OpenFlow service, which is sort of what it sounds like. It's using OpenFlow to put your data transfers on steroids, if you will. And it's you will see a similar kind of dramatic performance improvement to what Ezra and Martin have just shown us, but with a very different strategy for achieving that sort of improvement. And this is one of the exciting things about our current Genie deployment is there are enough different resources and enough different control paths that you can mess with different techniques for changing your performance. So that's about as long as I can stall. Did it?
Unfortunately, ION's still reporting that it's in setup, but I can guarantee you, if anyone saw the demo yesterday, it goes active, the transfer works. You have to believe me today. All right.
Thanks very much, Ezra and Martin.
Thank you.